So we're going to work on the topics in section 9.7, and the topic is partial fractions. So we're going to write rational expressions, so they look like a fraction, as the sum, addition, of rational expressions, again fractions, and those expressions have denominators that are linear or quadratic, because remember, we have a theorem that states that any polynomial can be factored into the product of linear and irreducible quadratic factors. So we've got a bunch of cases here. So the first case is when the denominator is a product of distinct linear factors. So presumably the denominator of example 1 factors into exactly 3 linear factors, since it's cubic. So let's just quick factor the denominator. So it looks to me like the grouping method is worth trying since there's 4 terms. So let's try that. So x squared times x plus 2 minus 1 times x plus 2. Oh, look at that, it's going to work. So we have x plus 2 times x squared minus 1, difference of squared. So we have x plus 2 times x plus 1 times x minus 1. So factor the denominator. So now we have 5x plus 7 over these factors. I'll write it as it was originally though. X to the third plus 2x squared minus x minus 2. And we're going to set it equal to the sum, so sum, addition, of 3, oops, that's plus, rational expressions, where the denominators are each of the factors of the denominator, which at a glance looks like, how do I know that's even possible? But we're going to try it out and see what happens. So the numerators are going to be a, b, and c, and we'll figure out what they are. So the numerator is equal to so think, if I'm going to add these together, I have to multiply each one by the missing factor so I get the common denominator. So I'd have to multiply this by x plus 1 times x minus 1, and I'd have to multiply this by x plus 2 times x minus 1, and I'd have to multiply this by x plus 2 times x plus 1. That's how you would get the common denominator, and likewise for the denominators. So the numerator would be equal to a times x plus 1 times x minus 1 plus b times x plus 2 x minus 1 plus c times x plus 2 times x plus 1. So I'm just going to simplify the right hand side, and it's still equal to 5x plus 7. So these factors multiply to x squared minus 1, and these multiply to x squared plus x minus 2, and these multiply to x squared plus 3x plus 2. So if I group the terms that have the same power of x, I'm going to get a plus b plus c times x squared. That's all the x squared terms, right? And then let's see what I have for the coefficients of x. So there's no x term here, there is an x term here. So I have b, so times 1, right? So b, and then, so that was this one. And then there's 3x, so c times 3, so 3c. So that's my x terms. And then my constant terms, so I have a times negative 1, so negative a. And then b times negative 2, so negative 2b. And then c times 2, So 2c, and those are my constant terms. And again, this is all still equal to 5x plus 7. Okay, so 5x plus 7 does not have an x squared term. Therefore, a plus b plus c equals 0, because again, there's no x squared term. And then b plus 3c is the coefficient on x, and my x coefficient is 5. And then negative a minus 2b plus 2c is my constant coefficient, and that is 7. So now I have a system of 3 equations. So I'm going to solve that, and I'm going to use the calculator. So I'm going to use an augmented matrix. So we know how to do this. So you would put it in, do all the magic, and we would find that a equals -1, b equals -1, and c equals 2. Again, we did that in the calculator. We solved this system by putting that augmented matrix that represents the coefficients of those equations into the calculator, doing RREF for reduced row echelon form, and reading off the solutions in the last column. So that's the solutions to that system. Therefore, the partial fraction decomposition here is a, which is -1 over x plus 2, plus b, which is -1 over x plus 1, so I'm just reading this off here, plus c, which is 2 over x minus 1, and that is equal to our original equation. I ran out of space, so I'm not going to write it again there. So now you should take a second or a minute and try this one, and I will put the answer up in a second. So this is the partial fraction decomposition of that problem. I hope you had fun with this problem. Now we're going to turn the page and work on the next one. So this is a different case. So it's all based on what the denominator can be factored into. So the denominator is a product of linear factors, but in this case, some of those linear factors are repeated, which is different from the previous example. So we're going to find the partial fraction decomposition of this problem. Here we go. So just like before, at first we're going to factor the denominator. Obviously, it's pretty much factored, but let's write it out. So we have x as a factor, and then we have 3 instances of the factor x minus 1. So again, always the first thing you want to do is factor the denominator. So now our original expression is going to be equal to the sum of, it turns out there's going to be 4, which is related to the 1, 2, 3, 4 factors. But it's a little different. So we're going to have a over x, that's familiar, plus b over x minus 1, that's familiar. But then our two other ones are going to be the product of the extra factors, if you will, and d times x minus 1 to the third. So there are 1, 2, 3 of them. So we have one term where the denominator has one of the factors, another where it has 2, and another where it has 3. And then we're going to do the same process. So the numerator, x squared plus 1, is going to be equal to a times, and we have to multiply by all the missing factors to basically get the common denominator. So that's going to be x minus 1 to the third, and b times, and the common denominator or the factors missing are x and then 2 of the x minus 1 factors plus c, and it's missing an x factor and 1 of the x minus 1 factors plus d, and the only factor that one's missing is x. The rest of it's the same, it's just going to give us a bigger matrix. So we have x squared plus 1 is equal to, and I do need to multiply this out, so this would be x to the third minus 3x squared plus 3x minus 1 plus b times x to the third minus 2x squared plus x plus c times x squared minus x plus dx. And now we're going to write out the sum of all the coefficients of each of the terms. So first we have an x to the third term. So those coefficients would be a x to the third plus b x to the third, and there isn't one here and there isn't one there. And the coefficient on x to the third is 0, so that's one of our equations. So we took care of the x to the thirds terms. And then I have my x squared terms. So I have a times negative 3, so negative 3a times x squared, negative 2 times bx squared, so negative 2b, plus c, so there's one of those, and that one doesn't have an x squared term. So the coefficient on x squared is 1. All right, now I'm working on my x terms. So I have, a little sloppy, that's 3. So a times 3, so 3a. So I took care of that one. And then there's 1 here, so b plus b, that's an x term. Here's an x term, so c times negative 1, so negative c. And then there's an x term here, so plus d. And that equals, there aren't any x terms here, so 0. And lastly, the constant terms. So I have a times negative 1, so negative 1a. That took care of that one. I don't have a constant term there. We used that one and forgot to cross it out, and there's no constant term there, so negative a equals 1. So again, I'm going to solve this in my calculator. I am going to write it down because this one is just bigger, so I feel like I should write it down for you. So what we have is 1a, 1b, 0c, 0d equals 0. Negative 3a, negative 2b, 1c, 0d equals 1. 3a, 1b, negative 1c, 1d equals 0. Didn't make my bracket big enough. Negative 1a, 0b, 0c, 0d equals 1. So we put that into the calculator, do RREF to solve, and we find that a equals negative 1, b equals 1, c equals 0, and d equals 2. So what does our expression look like? So remember, we started with x squared plus 1 over x times x minus 1 to the third, and we're going to end up with 4 terms. So our first denominator was x, and our a coefficient is negative 1. I'm going from up here. And then I have b, which is 1, and the denominator is x minus 1. And then c, which is 0. So I don't have to write that down, but I'm going to write it so to keep track. And then d, which is 2 over x minus 1 to the third. And we did it. Yahoo! Really fun. turn the page and we're going to work on another case. So again, we're looking at the denominator, and this one is going to have an irreducible quadratic factor. So you remember that from factoring polynomials, that it is possible for the fully factored form of a polynomial to have an or more than one irreducible quadratic factor, meaning it doesn't factor into more linear factors. So this denominator is actually pretty darn easy to factor because x is a common factor and we're left with x squared plus 4, the sum of squares. That has no real x intercepts. Excuse me, so that's not factorable. So irreducible, still have the same numerator. So that is an irreducible quadratic factor. So in that case, our expression can be split into the sum of two rational expressions where the denominator of one is the linear factor, the denominator of the other is the irreducible quadratic factor. The numerator with the linear factor has a numerator that's a real number. Remember in our previous two examples, A, B, C, D were all real numbers. Were real numbers, they weren't something else. So the difference here is that the numerator on the irreducible quadratic factor is going to be linear. So B and C are real numbers, but it's a linear expression. All right, so now we're going to go on with our same method as before. We just needed to have the setup right, and then the process is the same after this. So now we multiply by our missing factors to get a common denominator, and it's still going to be equal to the original expression. So I would need to multiply this by the missing quadratic factor, and then I would need to multiply, sorry, I didn't actually need the denominator because I'm setting numerators equal to each other. And then the bx plus c, the missing factor here is the linear factor. All right, and then just like before, I'm going to gather up the coefficients on my different terms. So I'm going to start with the quadratic. So I have a times x squared, and I don't have a quadratic. Actually, I do have a quadratic over here. I should have multiplied this out first. I'm going to multiply this out first. Bx squared plus cx. Ax squared plus 4a. Just felt like I should multiply that. All right, so I have a plus b are the coefficients on my x squared terms, and my x squared term has a coefficient of 2. All right, so I took care of my x squared terms. And then I'm going to look for my linear terms. That's not linear, that's constant. That's not linear, that's constant. Sorry, that is linear. So C is my linear term, and the coefficient on that is -1. Right, so I took care of that. That's constant. So my constant coefficient is 4a. So 4a is equal to my constant term, which is 4. So you could write a matrix and solve this, and that would be fine. But this is actually super simple to solve. 4 equals 4 tells me a equals 1. C equals -1 is clearly already solved. And then you can go 1 plus b equals 2. So that tells me that b equals 1. All right, so our system is solved. So now we're ready to write our expression as the sum of partial fractions. So our original expression, 2x squared minus x plus 4 over x to the third plus 4x, sorry about the dog making noise in the background, is a over x, and a was 1, plus bx, so b is 1, so 1x plus c, which is -1, so -1, which I could have written with a subtraction sign, all over x squared plus 4. So I'll just write this a little neater here. Woohoo, we did it! All right, we're going to turn and do the last page. All right. So the difference in this last, well, next to last example is that this one has repeated irreducible quadratic factors. So similar, but we've got more than one of these. So here we have 3 linear factors, and this is quadratic, and this is 3 quadratic factors. So take a minute and check. X squared plus 2 to the third. That is irreducible. Do you agree? Take a minute and try. Is it factorable? Does it have x-intercepts? Okay. What about this one? X squared plus x plus 1. So you might have to do some calculations to figure it out. My quick and easy way, if I'm not sure, is I just graph it in Desmos or my graphing calculator, and if it doesn't have x-intercepts, it's not factorable. So anyway, these are both irreducible. So we have 1, 2, 3, 4 irreducible quadratic factors. And this one is repeated. Okay, great. So I'm going to write it as a over x. So that was for the linear factor of x. So remember in an earlier example that when you had a repeated linear factor, you had to do one term for each of the repeats, and the denominator increases in exponent each time. So I have to have 3 terms because of the 3 linear factors that are repeated. So that takes care of those. And then this is an irreducible quadratic factor, so x squared plus x plus 1. And the numerator for a quadratic factor is going to be linear, so it can't be d, can't repeat letters, dx plus e. All right, and now I have 3 of these. So as you might guess, the denominator needs to be the quadratic factor, and we have a numerator that's linear, but it has different coefficients, so I'm up to a, b, c, d, e, f, x plus g, and then I'm going to write another term with a denominator that has 2 of those factors, so x squared plus 2, and the numerator is linear, so that was supposed to be a g. So now I'm up to hx plus I, and then I still have one more of those, so I need another term with a denominator that's one more of those irreducible linear quadratic factors. So now I'm up to jx plus k, and that's the form. Now clearly when we work this all out and find the coefficients, we're going to have a system with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you're going to have a system of 11 equations. with 11 unknowns. Thank goodness for calculators. But notice the directions said, write the form of the partial fraction decomposition. So that's the form. And we're going to stop. We followed the directions. Okay, so now we've got one more. So this example says use long division to write the partial fraction decomposition of. So here's the thing. This is not easily factorable. So we're just going to dive right in and do what the directions say, which are to use long division. So I'm going to dive in and do long division. So here's the divisor. I'm going to set up my long division problem. 2x to the fourth, and so on, and being careful. Alright, so x to the third times what gives me 2x to the fourth, so that would be 2x. Multiply it by the divisor, and I get 2x to the fourth plus 4x to the third minus 2x squared minus 4x, and then I subtract, cancel, 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 x minus negative 4x is 5x, 7 minus 0 is 7. So the answer to my long division problem is that this expression equals 2x plus 5x plus 7 over the divisor, x to the third plus 2x squared minus x minus 2. So now what I need to do is the partial decomposition of this expression, because that was a big mess, right? But this is simplified because we took out that term that's a 2x. So we should have to do this. But notice that we did this problem on the first page. So this is example 1, just this part of it. So we did that already. So we know what that answer is. So it's going to be 2x plus 2 over x minus 1 plus negative 1 over x plus 1. This is from the earlier problem. Plus negative 1 over x plus 2. Woohoo, we did it. Yay, us. So I also want to point out that the homework problems are listed up here, and there's not very many of them. So good luck, and good luck on your